James Webb spots a strange anomaly on 3I Atlas.
Things have gotten very, very interesting.
An intelligent visitor from another solar system.
3. Atlas wasn't supposed to be anything special. It was expected to behave like every other interstellar visitor. A cold, predictable block of ice drifting in from deep space. That was the assumption, until the James Webb Space Telescope focused on it. When the first spectral data came in, everything changed. The readings didn't match any known comet model. In fact, nothing about its behavior lined up with what science had documented over decades. We've only known about this object for a short time, but from the beginning, something felt off. Scientists immediately noticed characteristics that didn't fit into any established category. James Webb had detected physical behaviors that modern comet science simply cannot explain. So now the question hangs in the air. Is 3I Atlas just an exotic chunk of ice, or the first sign of something intelligently engineered? Once that possibility exists, every new measurement only deepens the mystery. Normally, when sunlight warms a comet, water vapor is the first thing detected. This pattern has been consistent for years across countless comet observations. No matter the size, origin, or age, water always dominates early outgassing. That rule has been so reliable that scientists built their entire formation and evolution models around it. But when James Webb analyzed 3I Atlas, those expectations collapsed. The chemical fingerprint came back completely reversed. Water wasn't leading the spectrum at all. Instead, the strongest signals were carbon dioxide, and the ratio between CO2 and water was unlike anything ever recorded. This wasn't a small anomaly. It was a discovery so extreme it challenged the very framework of comet science. In every known case, water ice dominates because it forms easily across a broad temperature range in young planetary systems. CO2 ice forms farther out, in colder regions, and carbon monoxide even farther. Yet 3I Atlas doesn't follow those rules. It's behaving like something that formed under conditions we've never observed, or perhaps something designed, not naturally formed. And now the world is watching. In a typical comet, the layers of frozen gases form a natural order. Water ice sits closest to the surface because it responds to heat first. But 3I Atlas didn't follow that rule. It behaved as if the water layer was sealed away or inactive, while carbon dioxide escaped freely and aggressively. Scientists using the Webb telescope checked the data multiple times, and each observation confirmed the same unusual pattern. Nothing like this reverse chemical ratio has ever been seen before. Not in Oort cloud comets, not in Kuiper belt objects, and not even in the interstellar comet Borisov. Then things became even stranger. The telescope detected carbonyl sulfide, a gas that only forms when sulfur-based ices or minerals are exposed to extreme cold or intense radiation. This compound is extremely rare in typical comets. Its presence suggests that 3I Atlas either formed in an unusually harsh environment or went through a type of cosmic processing that isn't part of any known comet evolution pathway. Add to that the strong signal of carbon monoxide, and the mystery deepens. Carbon monoxide only freezes in extreme cold. For a comet to contain so much of it, the temperatures during formation must have been far below those found in normal comet-forming regions. Spectral readings from Webb are precise. They reveal exactly which molecules are present and in what amounts. The data shows no errors and no signs of contamination. The chemical signature is genuine. The problem is, no known comet behaves or looks like this. Oort cloud comets are rich in water. Kuiper belt comets also contain abundant water with minor variations in organic molecules. Even Borisov, which came from another star system, followed the expected water-dominated pattern. But 3I Atlas does not belong to any of these families. Its chemical makeup ignores the standard hierarchy entirely. By current scientific models, a comet with this much carbon dioxide and so little detectable water shouldn't exist. If water isn't leading the outgassing, then its internal structure must be fundamentally different. Scientists have begun proposing theories, but none fully explain the data. One idea is that 3I Atlas formed far beyond the typical ice line in its home system, a region cold enough for massive amounts of carbon dioxide to freeze while water behaves differently. That could explain the CO2 dominance, but it still doesn't clarify why the water layer appears suppressed. Another hypothesis suggests that the comet's outer layers were altered by billions of years of radiation during its journey through deep space. High-energy particles can destroy water ice and leave behind more radiation-resistant molecules, like carbon dioxide. A thick crust of processed material might be hiding deeper water, waiting for stronger sunlight to break through. For now, the truth remains unclear. But one thing is certain. 3I Atlas is rewriting the rules. This idea could explain some of the early findings, but it still doesn't fully account for the extreme spike in carbon dioxide. The Webb telescope detected far more CO2 than surface processing alone should produce. A third possibility focuses on structure. The nucleus may contain fractured layers or sealed chambers that trap heat unevenly. If sunlight can't reach the deeper ice, the water remains frozen and inactive, while carbon dioxide escapes through vents or surface cracks. But for this to be true, the comet would need an internal layout unlike anything seen in the comets we've studied. Right now, there's no way to confirm this. It's just a hypothesis, not a conclusion. The key point is that none of the proposed explanations match the data perfectly. The chemistry forces scientists to rethink what an interstellar comet can be. It doesn't look like an oversized version of Borisov, and it doesn't resemble any comet from our own solar system. Instead, it sits far outside the known classification chart. 3I Atlas carries a chemical signature that doesn't fit any current model. It isn't just unusual, it breaks the assumptions we use to categorize icy bodies. Webb didn't detect one strange molecule. It detected an entire chemical pattern that shouldn't exist in a naturally formed comet based on what we currently understand. And chemistry is only the beginning. The thermal behavior is even more confusing because it defies basic physics. When the Webb telescope measured the comet's temperature, it found something unexpected. 3I Atlas was aggressively outgassing at a distance where it shouldn't have enough heat to do so. Under normal conditions, as a comet approaches the sun, sunlight warms the surface and triggers sublimation, where frozen gases turn directly into vapor. The closer to the sun, the stronger this activity becomes. Farther away, it should be weak or non-existent. But 3I Atlas didn't follow this rule. Webb's infrared instruments detected strong CO2 release far earlier than expected. The brightness increased rapidly, and the carbon dioxide signal surged while the water signal remained surprisingly weak. It didn't look like a gradual warming. It looked like something had activated suddenly, as if a switch had been turned on. This creates what scientists now call a thermal mismatch. The outer surface is acting warm enough to release large amounts of carbon dioxide, while the deeper water-rich layers remain frozen. That breaks the understanding that heat should move inward and activate different layers in a predictable order. Normally, once a comet crosses a certain distance from the sun, water ice should begin outgassing. But here, the opposite happened. Carbon dioxide activated first, and water lagged behind. At this point, the mystery isn't just chemical, it's mechanical. It's about how heat moves through the comet's interior, or in this case, how it doesn't. One theory is that 3I Atlas has an insulating layer, a porous crust formed from radiation exposure during its long journey through interstellar space. Such a crust could block heat from reaching deeper water ice. Insulation layers aren't unheard of, but they're usually associated with old comets that have made repeated passes near a star, not a first-time visitor from another system. Another idea focuses on internal geometry. The nucleus may be uneven or cavernous, directing heat toward the surface while isolating deeper layers. Picture a sponge-like interior with sealed pockets. CO2 near the upper layers could escape rapidly while deeper water remains untouched. This could explain the delayed water signal. But once again, these theories only explain fragments of the data. None of them fully solve the puzzle. The thermal mismatch in 3I Atlas is too extreme to be explained by a simple crust of insulation. And the way the gases escape suggests something more organized than random cracks or hollow spaces. If the comet is fractured, the fractures may be arranged in a structured pattern, almost like layers peeling apart with clean boundaries. That possibility leads to a bigger question. How did this comet form in the first place? One hypothesis is that it may have formed near a highly active young star. In such an environment, Intense ultraviolet radiation could alter the developing surface of a comet, changing how heat is absorbed and distributed. A radiation-processed shell could heat up quickly while preventing warmth from penetrating deeply, which aligns with what the Webb telescope observed. But there's a problem. Massive, energetic newborn stars burn fast and don't last long. For 3I Atlas to survive such an environment, get ejected from its home system, travel through interstellar space for millions or possibly billions of years, and still retain these unusual properties. It's possible, but it sits at the edge of our current understanding. Then comes the most telling detail. If the delayed water activity were just a thermal lag effect, the water should have begun outgassing normally once the comet approached the sun. But that didn't happen. Even during peak activity, the water signal remained unusually weak. Later telescope confirmations showed water did eventually appear, but still far below expected levels for an object of this mass and distance. This suggests 3I Atlas isn't just delayed in its response. Its thermal behavior may be permanently different. That's why some astronomers now believe the object may not just be chemically unusual. It may be structurally unique in ways we've never modeled. It could be layered differently, built like a composite, or shaped by radiation far more intense than anything our solar system provides. These ideas are still speculative, but the data isn't. Webb recorded a comet releasing large amounts of carbon dioxide at a distance where it should still be frozen, while water ice barely reacted. That part is undisputed, and it adds to a growing pattern. 3I Atlas is not behaving like any known comet class. None of this automatically suggests artificial origin, and scientists have been careful to shut down that kind of speculation for now. But even within natural physics, the numbers don't align. The object heats too quickly, releases gas too early, and somehow insulates its deeper layers in a way that current comet models cannot explain. For something expected to be simple and ancient, its behavior is anything but. And when an instrument as precise as Webb encounters confusion, it means the universe is presenting something real, something measurable, something outside our existing categories, something that, quite simply, should not exist. When 3I Atlas was first detected moving across the sky, astronomers followed standard procedure. They recorded its motion, ran trajectory models, and refined the results using data from both US and European observatories. The final orbital solution was unmistakable, a clean hyperbolic path. There was no curve, no looping return, no gravitational arc pointing back to our system. Its speed and direction made one thing certain. 3I Atlas did not come from the sun. Interstellar visitors are no longer unheard of. First came Oumuamua in 2017, then Comet Borisov in 2019. But 3I Atlas brought something new, not just another object from beyond the solar system, but one with a distinct galactic origin. Its trajectory traces back to a region called the Milky Way's thick disk, an ancient stellar population. Stars in that region contain very few heavy elements, because they formed early, long before supernovae enriched the galaxy with metals. Most objects there are 5 to 10 billion years old. That means the material inside 3I Atlas, whatever it is, may be older than Earth, older than the Sun, and older than every planet in our system. This age estimate isn't speculation. It comes from orbital dynamics and stellar motion models. Its velocity and angle match the slow-moving, high-inclination population associated with the thick disk. The most likely scenario is that it formed around a long-gone star, was ejected by gravitational chaos, and has wandered through interstellar space ever since. But that's where the mystery deepens. If it came from such an old, metal-poor environment, its chemistry should reflect that origin. Scientists expected a simple mixture of primitive ices, water, carbon dioxide, carbon monoxide, and perhaps small traces of lightweight organic compounds. Instead, the James Webb Space Telescope detected chemical signatures that don't match a metal-poor formation at all. The molecular profile looked processed, shaped by conditions richer in heavier elements, or by events that require more complex environments than those typically found in ancient galactic regions. In other words, 3I Atlas doesn't chemically match the place the universe says it came from. Nickel is normally trapped inside dense minerals and only released through intense heat or violent processes. So finding it in gas form, and at levels this high, is extremely unusual for any comet. It's even stranger considering 3I Atlas was expected to come from a region with very few heavy elements. This isn't a subtle measurement or statistical stretch. The nickel signature stands out clearly in Webb's spectrum. What doesn't appear alongside it is iron. In comets from our solar system, nickel and iron always appear together in stable, predictable ratios because they come from the same mineral families and are liberated under similar conditions. But in 3I Atlas, that balance is broken. So now there's a conflict. Its trajectory suggests an ancient metal-poor origin. Its chemistry behaves as if it came from a younger, more metal-rich and more violent environment. Both can't be true, at least not under current models. This contradiction has sparked ongoing debate. How can an object born in one of the galaxy's oldest neighborhoods look chemically processed, almost modified as if it came from a more evolved system? One hypothesis is that 3I Atlas may have lived more than one cosmic life stage. It could have formed in a cold, quiet region billions of years ago, then later drifted through a denser or more energetic star field. There, radiation, shock waves, or stellar winds might have altered its chemistry. That would explain its unusual composition, but it creates new problems. Objects exposed to that level of processing usually don't survive intact. They break apart, lose their ices, or become inert fragments. Yet 3I Atlas is still active, stable, and carrying both ancient ices and high-temperature chemical signatures. Another possibility is that it once passed close to a massive young star. Such stars release intense radiation capable of modifying surface chemistry from afar. If the comet traveled near one, it could have acquired its nickel-rich chemistry through exposure rather than formation. But again, timing makes it difficult. Massive stars burn out quickly. For 3I Atlas to pass through such a system unharmed and exit without melting or fragmenting is possible, but hard to fit into existing models. Then comes the simplest, but still unproven interpretation. Maybe 3I Atlas isn't uniform at all. Maybe it's a composite object, formed from materials that originated in different environments and later fused together through collisions or gravitational interactions in the early galaxy. That could explain layered chemistry. But even that idea hits a wall. How could such a mixed, fragile structure stay stable for billions of years, only to suddenly erupt with intense activity the moment it neared our sun? At present, there is no single model that explains everything. 3I Atlas remains a contradiction wrapped in data, ancient in age, but chemically altered. Metal-poor by origin, but metal-rich in signature. Structurally frozen for eons, yet violently awake now. It is in every sense an object that refuses to fit the rules. What remains now is a puzzle. Its orbital track suggests one age, yet its gas emissions point to another. Its expected birthplace doesn't line up with the minerals inside it. On paper, its trajectory says it came from a calm, ancient region of the galaxy. But its chemistry tells a story shaped by heat, pressure, and violent environments. And that contradiction isn't small. Comets are supposed to be simple records of their past, a frozen archive. Their paths reveal where they originated. Their chemical makeup reveals how they formed. But when those two messages disagree, the entire system of classification breaks. If an object like 3I Atlas exists with these inconsistencies, then it's possible that others like it have already passed through our catalog unnoticed, misfiled, or misunderstood. Right now, no single explanation fits everything we see. Researchers are still gathering data, adjusting computer models, and comparing measurements. But so far, one conclusion stands out. 3I Atlas's chemistry and its origin story do not line up. That mismatch isn't a small scientific anomaly. It is a deep structural challenge to how we understand interstellar objects, which means that somewhere in its long history, something extraordinary happened, something that defies our standard rules, something unaccounted for, something that shouldn't exist, and yet does.